China, a lecture series. And our next lecture in the series will be Thursday of this week. We'll have a visitor from Peking University, Professor Lu Ji, presenting case studies from China on living in harmony with nature. It'll be Thursday, 4:30 in Lewis Simpson. 2 weeks after that, just to remind you, October 17th, we're partnering with Brazil Lab and also peers to present a conference that we're calling Amazonian Leapfrogging, looking at the future of the Amazon from the perspective of both Brazil and the planet. And a week after that, October 24-25, will be PEI's 25th anniversary conference. We're calling it the Princeton Environmental Forum, and that will be in Richardson Auditorium. You're welcome to all of those events. I hope to see many or most of you there. All right. Among other things, at this environmental forum, we're going to have a number of panels that are moderated by faculty. Today's speaker, Gabe, will be one of the moderators. He'll be looking after a panel that has the title, "It's Getting Hot Out There, Weird Weather and Other Climate Change Anomalies." So that tells you a little bit about Gabe's interest. I'm sure you all know Gabe already, but he's a professor in geosciences and in PEI. His research broadly is around climate science with a focus on extreme events, hurricanes, mechanisms of precipitation variability, and detection and attribution. He actually does many things. One is to participate in a sort of rapid analysis series put out by the World Weather Attribution, which is an international effort to analyze and communicate the influence of climate change on extreme weather. The latest publication just came out very recently, focused on the extreme rainfall associated with Tropical Storm Imelda, which you may recall hit Texas about 10 days ago. So the idea of this, and Gabe does an amazing job of this, is to get information out quickly while it's still on your mind and discuss the scientific underpinnings of how you can provide attribution in regard to climate change.
That one was a shoo-in.
It was a third one in 4 years, so.
Anyway, you can have that conversation today. Last thing I usually do is to list the awards. Gabe has many awards. I just picked out a couple of them. He's got the NOAA's Al Britton Award for Outstanding Science Communication. He has the AMS, the American Meteorological Society, Meitzinger Award, quote, for outstanding contributions to the understanding of tropical climate variability and change. He's a recipient of the AGU Ascent Award, which is to reward exceptional mid-career scientists in the fields of atmosphere and climate science, where the recipients have to demonstrate excellence in both research and leadership. And the last thing I'll point out is that for at least the last 5 years, Gabe has been recognized as a highly cited researcher, meaning that he's had multiple highly cited papers that rank in the top 1% in terms of citations. That's not easy to do, I think, for me, at least for a single year. 5 in a row is amazing. So we have a real expert here today to tell us a little bit about his work on hurricanes. So please join me in welcoming Gabe Vecchi.
All right, well, thank you. Thank you for coming. Thank you. I had to press a button. It's button number 3 for the next one of you that is. And then you hit the close button for the next person that's here. So what I'm going to try to do today, I had these visions of throwing everything I've done, including the things I'm most excited about, at you. And as I started looking at it, I realized a lot of the things I'm really, really, really excited about are pretty inside baseball. And in the spirit of PEI and trying to appeal to an interdisciplinary audience to try and start a conversation, I'm going to try and hit a few points along the way that I think make a story. But please, I'm in 407 over here. I sometimes even answer my email. So if you want to have a broader, longer conversation, please reach out. I'd love to talk. So roughly what I'm going to talk about today is how hurricanes, tropical cyclones in the Atlantic have changed. I'll try to say a little bit about why. And try to say a little bit of what we know and how we know about what's going to happen in the coming decades. So many of us have been in New Jersey for at least since 2011. So you remember Irene, and you remember Sandy, or if you don't remember them in person, you remember them from the TV. But there's been a number of other tropical cyclones, so I hope that your presence here and your general existence on this planet means that you're somewhat aware of tropical cyclones and what they can do. They are large storms. They have space scales of hundreds of kilometers. They're characterized by having very strong winds. They are symmetric. They have what we call a warm core. They have warm air above the low pressure system. And you can see a very beautiful image on the right over there. And that is a tropical cyclone. They are gorgeous. They're also extremely dangerous, right? And so I'm going to, and this is one of these things when talking about tropical cyclones, it's easy to fall into this sort of scientific curiosity, how beautiful they are. But we need to remember that these are dangerous things that do impact people. Sandy, there was a fatality in Princeton. We're not even on the shore. And so, trying to balance those two, the sensitivity and sort of the beauty that's here. So here are some of the things that cyclones can do. They can push salt water on land, create a storm surge. And when that water is moving towards you, it picks up debris, and it becomes very dangerous. Another thing it can do is that it can dump a lot of fresh water on you from atop. And that water, if it doesn't infiltrate into the ground or found a way to get channeled to useful places, can become dangerous and give you flooding. And then, of course, there's a direct impact of wind. And these three things are generally happening at the same time. Okay? They can also spawn at landfall tornadoes within them. Tropical cyclones and tornadoes are very different phenomena. They have very different dynamics, but sometimes you'll find tornadoes embedded inside tropical cyclones. The mechanisms behind that sustain tropical cyclones are a ubiquitous feature in the tropics and actually in the poles as well, but that's a topic for a different day. They arise due to a feedback between wind speed, so evaporation. So when we blow in our coffee or our soup to cool it, we increase the evaporation through the wind. The ocean and atmosphere do the same thing. You get more evaporation. That evaporation provides water to rain. That rain heats the column of air. So I said there's a warm core, which lowers the pressure more, which speeds up the winds, and you have sort of this runaway effect. There are some theories that allow us to predict what the upper bound on wind speed is for a tropical cyclone. This is potential intensity theory. It's often interpreted in a Carnot heat engine analogy, but I'm not really going to get into that. One of the key ingredients for a tropical cyclone is warm water. Warm is a relative term. As best as we know, you can get tropical cyclones even in an almost frozen planet. The water just has to be warmer than almost frozen. They also, though, need a moist atmosphere, and they need relatively quiet winds, because otherwise the storm, as it tries to organize into this symmetric warm core feature, will get torn apart or have dry air put inside of it. Okay, so there's a number of factors that tend to influence tropical cyclones. When you look at any individual tropical cyclone, and this is an animation of cloud top temperatures during Dorian. This was Gan show. I saw this from him, and it's really nice. Shows how you have this sort of semi-organized, it's relatively organized convection starting in the low tropics for Dorian. You start getting something that looks like rotation as it makes it past the Lesser Antilles. There we are going past Puerto Rico. Then you start getting very clear rotation. You see the counterclockwise rotation in that storm, and then a little bit, you start developing an eye. Do you see that eye in the center? We don't really know why there's an eye, but we know once it's there, it maintains itself. And as Dorian makes its way over the Bahamas, it decides to hang around, and hang around, and hang around, and hang around, and hang around. And then it moves up the east coast of the United States, totally bypassing Alabama. And as it moves up the east coast of the United States, it turns asymmetric. The rain moves a little more towards the left than to the right of the storm. It's a process known as extratropical transition. And what it does is it tends to move rain landward as the storm moves up the east coast of the US. Here's just an example. You can see there's a lot going on in these storms. They're very much weather events. Every detail matters. Yet, we're able to say a lot about tropical cyclones without considering every detail. All right? We just have to phrase the questions correctly. That was a hurricane. Tropical cyclones, as I said, are ubiquitous. They're everywhere in the tropics. Here's from observations. Color-coded by intensity at the time where these storms were. This is about 30 years of storms. The redder colors are the Category 5 storms. This is Saffir-Simpson. This is based on wind speed. Category 5 is 70 meters a second or greater, so 140 knots or so or greater. It doesn't have an upper bound because at the time that this scale was created, there were so few Category 5s, and anything much more than 70 meters a second just didn't show up. So what's the point of having a Category 6? That's no longer the case. We've had multiple storms that if you had a sequence of spacings that followed all the categories up to that would have been Category 6. Patricia's one of them, but there's been many others. So you can see that tropical cyclones do not form on the equator, right? They don't form on the equator because they need to draw on the Earth's rotation, and the equator is parallel to the axis of rotation of the Earth. So we can't draw for the horizontal winds on that. They also tend, at least in the northern hemisphere, to, in the low tropics, propagate to the west, westward. And then they're also drifting slowly to the north. And then once they hit the middle latitudes, they recurve back to the west. What that reflects is two processes. One, which is called beta drift. It's due to the sphericity and rotation of the Earth. That tends to move storms poleward and westward. And then the mean winds that are easterly, that is from the east in the low latitudes, and westerly in the middle latitudes, also push the storms around. Okay? So a number of other features. The strongest storms on our planet are in the West Pacific, where also the warmest waters are right now. There are some pretty strong storms in the Caribbean and Gulf of Mexico. The Atlantic is a player, but it's not the big player. But for the United States and for many people, it is the important thing. And so we will focus on the Atlantic. I've been here at Princeton for a while, Princeton, the town, and the university as a lecturer before coming here on the faculty. I was at GFDL for 13 years, and last February 2017, I came on the faculty of Geo and PEI. And this was where the U.S. landfalling hurricane record was at the time, and there seemed to be something really, really interesting going on. So up to 2016, this is the number of major, and these are the storms that are 50 meters a second maximum winds or stronger, storms landfalling in the U.S. from 1878, which is when the U.S. Signal Corps, the predecessor of the Weather Service, was tasked with monitoring tropical cyclones by Congress, all the way to 2016. And most years, you get either 1 or 0 storms hitting the United States. Every now and again, major hurricanes hit 2 times in a season. A few times, they hit 3 or 4 times. But interestingly, from 2006 to 2016, there was no major hurricanes hitting the U.S. When we saw this for 5 years, we said it was silly, no reason to pay attention. Once we saw it for 10 years, we said, oh my goodness, this needs an explanation. And so a number of us rushed in to try and explain it. And that's where my thinking was. What is going on with this drought in 2016? That was not just my thinking, it was the thinking of science and the media. So here is from Time. Scientists have figured out why big hurricanes keep missing the US in January 2017. And August 2016, the US coast is an unprecedented hurricane drought, why this is terrifying. And there was a number of papers that were in press at the time explaining the drought. Nature got the memo, and gave us 2017, where we had 2 major hurricanes hitting the mainland United States, but one also hitting outlying islands of the United States, the Virgin Islands and Puerto Rico, actually 2 hitting the Virgin Islands. One of them, Maria. Puerto Rico is still recovering from Maria. And then just to make sure that we didn't keep talking about the drought, 2018 came around, and we had 1 major hurricane making landfall and 2 hurricanes making landfall over the continental United States. So that when you now look at the 1878 to 2018 hurricane record, yes, there's a gap at the end, but it seems a lot less of a prominent thing to understand. Okay? The other thing is, over that period that there was a drought in the US, there was plenty of hurricanes making landfall all over the Atlantic. I mean, the United States, we have this habit in this country of sort of making us the world. Baseball, the national pastime, all of a sudden has a World Series, right? I mean, I enjoyed it last year. Yeah. But, you know, for those of us that follow baseball, we realize there's also the Caribbean Series, right? And much like in baseball, we need to consider things outside of the United States when interpreting hurricanes. So let's put this series on a larger context. Let's go to the National Hurricane Center, download their data, and start counting how many major hurricanes are there in the Atlantic every year since Congress mandated that the Signal Corps track major hurricanes. And when you do that, you get this time series. It does not look like the US landfalling series. It looks very different from it. There was plenty of major hurricanes in the Atlantic over this period. So talking about the drought was a very myopic conversation, right? And some of you may notice a trend. For those of you that don't notice the trend, I drew the trend up there for you. So now you see it. And that trend is significant like you wouldn't believe. It is, you can test it against the time series all you want, and it's hard to explain by resampling the time series or any sort of noise that is likely to be composed of that time series. So it's something that bears explaining. Remember when I told you that hurricanes like warm water? Strong hurricanes really like warm water. And so one of the thoughts that many of us had, because there's a sort of a reasonable expectation that hurricanes should like warm water, and there's some theoretical thinking that hurricanes should like warm water. There should be more major hurricanes as the planet warms. And we've seen the planet warm. And models tells us that the planet should warm and give us more major hurricanes when it warms. We said, oh my goodness. Is this from the warming of the planet that's happened over this period? So one possible explanation. Another possible explanation is that this didn't actually happen. All right? So this is the recorded number of hurricanes in the Atlantic. Right now, when you go see what the Atlantic is doing, you can look at beautiful satellite images from all sorts of satellites, all sorts of wavelengths, geostationary, polar orbiting, all sorts of other things. Aircraft, ships, this, that, and the other. That was not available over here. It was definitely not available over here, and definitely not available over here. Now, I've spent a bit of my career working with Tom Knutson and others and trying to understand the hurricane record. We finally were confident enough to tackle the major hurricane record in the Atlantic recently, over the past couple of years. And so what we did is a game that we've played before. First, we looked at where ships were in the past, because ships before the satellite era were the only way to see hurricanes. On the top right are the satellite era hurricanes. You see where they happen to be. On the top left, my right. This right, top, shows the hurricane tracks 1878 to 1914. The ship tracks, sorry about that. Ships. These are where vessels were. Red colors are where there's a lot of ship density. And you should notice that there is almost a mirror image or a negative positive quality between the top two. Now, it's not that the ships were so clever that they decided to make their shipping routes go around the cyclones, but rather, there wasn't really good commercial sense to try to sail into the Caribbean from Europe on your way to Asia or the western coast of the United States or somewhere else. Instead, what you wanted to do was hug the west coast of Africa as close as you could so that the east coast of Brazil that's sticking over, because America is tilted, right, zonally, there's South America and North America don't line up in the north-south direction. The ships ran along that coast. 1914, war started, but also a canal opened, a palindrome. Man, a plan. Yeah. And we all of a sudden have all these ship tracks going into the Caribbean and Gulf of Mexico. And then after World War II, as there's a lot of development and really large-scale oil exploration there, then there's a lot more shipping going into the Caribbean and Gulf of Mexico. A game you can do is you can't make the past observing system any better than it was. But what you can do is degrade the modern-day observing system to be what it would have been in the past and ask how many storms would have been missed had they occurred in the past. We know they occurred in the present, right? But they could have maybe slipped through these ship tracks. So you can play this game. You can blow present-day storms through ship tracks, count how many times they're missed, and ask what that does to the hurricane record. And shown here is now a new record. This is smooth just to make it easier to digest. The gray line is the raw number of hurricanes every year that are major in the Atlantic. And you see that clear trend. There is some variability, but it's clear that as you go into the present, there are more than in the past. Some decadal variability. If you look at the red line, that's once you account for changes in observing practices, the trend goes away. The trend in recorded storms is major hurricanes is entirely explainable by changes in observing practices. That doesn't mean that there was no trend. It just means that given the observing system that we've had, we can't exclude that there hasn't been one, right? And the burden should be on showing that there is one, okay? So that's what observations are showing us. Okay. Now, observations are fun, but even more fun is playing with computers. And this is our new lab. It's fancy, it's fast, it's got a logo. It's Princeton's new supercomputer, Tiger, and it's just across Route 1. And it's a place where we can do a bunch of experiments that we can't do in nature. The way we do that is we use global dynamical models. These are mathematical representations of the laws that govern fluid flow in the atmosphere and ocean, thermodynamics, radiative transfer, aspects of land ecosystems and hydrology, sea ice, and then how all these things interact. They're sort of climate, they're just math and physics, and they allow us to ask questions about how the planet would respond to perturbations that we can't do in a sort of a clean manner with our planet. We are perturbing it, and we are slowly seeing what we're doing to it, but it would have been nicer to look ahead and maybe decide to do different. So what we have is these models. A key aspect of them is you have to discretize the equations. So you have to turn the music into a CD from an LP. You have to take the photograph and turn it digital from well, you know, listen, there was things that were better before, young people. So what we do is we have to make the world into little boxes, and our ability to correctly represent the full precision is limited by the size of those boxes. Also, the types of phenomena that we can represent is also limited by the size of those boxes. You can't well represent something that is a couple hundred kilometers across if your grid size is 1,000 kilometers across, right? But nowadays, computer power, including Tiger, allows us to run high-resolution models that have the spatial scale sufficient to represent hurricanes. Here's an image from a model ran on Tiger. This is a climate model developed at GFDL, our buddies across Route 1. They're a NOAA lab, and they're close partners that we have. And what it shows is atmospheric water vapor, just a snapshot of it from a model. And for any of you that look at satellite images of water vapor, this is plausible. This, just to look something pretty, I like it. It's almost Rothko-ish, but not quite. You know. And you can see some extratropical storms and atmospheric rivers. You can even see some tropical storms there, those little black swirly dots in the northern and southern hemisphere. You can see the low water vapor over mountains. This is all really nice. And these types of models can now represent tropical cyclones. Here's a figure from a paper by Hiro Murakami. And what it shows is tropical cyclones in observations. I showed this before. And this is from a climate model developed at GFDL. And what you see is that there is at least qualitative and maybe even some quantitative correspondence between the two. And the nice thing about having a model now like that is that we can directly inquire what it says hurricanes and tropical cyclones would do to some perturbations that we may have to wait quite a long time to actually see the observed signal come out. So a standard thing that we can do is we have projections for the 21st century of what CO2 and other gases in the atmosphere and ozone and land surface and all sorts of things should do, and you can impose that on the model, and you can see how different aspects of it change, one of them being tropical cyclones. And one of the things that comes out, and this is from a paper led by Maofang Liu, who's in civil environmental engineering, works with Jim Smith and I, and Hiro Murakami, who's at GFDL. And what we did is we asked, this is the density of tropical cyclones. That is, how likely are you to find a tropical cyclone near a place? This is what it is in the present day in the model. So you tend to have a lot of tropical cyclones in this area. It's a little similar to observation, slightly displaced, but not bad. And you can ask, how does this density change over the 21st century if we continue to increase greenhouse gases, reduce atmospheric aerosols, et cetera? And what you find is that there is a predicted reduction of hurricane activity over the western part of the basin, and a somewhat increase on the eastern part and along the northeast coast and even in Europe. This northeastward shift is actually emerging in a number of studies and projections. And now this is model output. If you look at observations, and this is a paper looking at observations that we did a few years earlier. If you look at the raw data from the National Hurricane Center or the data adjusted for missing tracks, there is at least a rough correspondence where the eastern part of the Atlantic is either getting more active or remaining close to the same, and the western part is becoming less active. So, and this is a trend over the 20th century. This is what we should expect over the 21st century. And maybe this shift in tracks is happening. Now, that's cute. It seems that maybe it's shifting into the open Atlantic, so big whoop, who cares? Well, I think we should care, because one of the things that goes on in these same experiments is that if you look at tropical cyclone rainfall, there's a big increase in tropical cyclone rainfall predicted on the northeast of the United States. That tropical cyclone rainfall increase is not associated so much with, well, it's associated in part with an increase of tropical cyclones in this area. And this is an area that doesn't usually get hit by tropical cyclones. it gets hit by things that used to be tropical cyclones and undergo a process that we know as extratropical transition. Tropical cyclones tend to rain more in a much more concentrated way. Extratropical cyclones tend to have a much broader rainfall. What seems to be going on in this model is that there's a poleward shift in the latitude at which extratropical transition happens. And so the tropics are moving into us in this model. So although maybe this seems like good news, blues on the right, on the left, and reds on the right, seems to be a tendency for an increase of the tropical nature of storms as they move northward. All right. So the character of rain from storms may be changing, but I started out talking about intensity. These same models, some of these same models allow us to say something about intensity. And here's an adaptation from a paper led by Kiran Bhatia. He is now working at BP, but he is a weather guy and a climate guy. And what he shows here is the change in major hurricane incident, category 3, 4, 5, predicted for 2081 to 2100 minus the present day. And this is measured in years per decade in which you have a major hurricane coming over you. 0 means it's the same amount as present. Positive means more, and negative means fewer years per decade with a major hurricane. All these reds along the Antilles, Florida, Alabama, and Georgia, and then up the East Coast are suggesting that major hurricanes hitting landfall should become more frequent in the US. Not only that, this is another way to look at the same data, and it's the fraction of years or the return. So how the future value compares to the present value. 100% is that they're the same value, right? The same number of years in each one. 1,000 means that there's 10 times as many in the future. Black means that there were no cases in the control experiment, but yes cases in the future scenario. We're seeing a prediction that there's a substantial few 100% increase in the end of the 21st century in the number of years that a place will experience a major hurricane, and including certain places that in the control climate you don't get any, or in our experience you don't get any. That's Newfoundland over here, I think, and now in the future climate you could get some. This becomes a challenge. Societies are generally adapted to the climate they experience and small deviations from that, right? A New Jersey house knows that there's winter. A Michigan house really knows that there's winter. A Florida house, or houses I grew up in, don't account for winter. We account for other things. We want to cool, right? And houses over here, yeah, they get winter storms, but they don't get major hurricanes. So this is an issue. Not only that, tropical cyclones sometimes undergo this thing called rapid intensification, RI. Some of you may have heard about this because many storms over the recent few years have made rapid intensification. That is when a storm's intensity changes by many tens of meters a second over less than 24 hours. And because of that, it makes it a challenge to prepare. You're going to bed, you have a category 1 heading your way, you wake up, it's now category 3, right? They're very hard to predict on multi-day timescales, and so it's not something that we should enjoy. The model is saying that the fraction of storms making rapid intensification should increase over the present century everywhere. Everywhere that there's a change, it should be for an increase over the present century. So not only are we seeing more storms along the East Coast that should be major in the future, but they are getting there rapidly. And so we'll present a challenge. And I think what one of these things tells us is that we should be looking at really investing in improving our weather forecasting capability, right? So that we can better react to these types of storms. Now this is all a prediction and it's all from a model, and I told you the model looks nice. But I also told you and showed you that we have no change in US landfalling hurricanes of the 20th century. And we all know the planet's been warming. So what gives? Right? Look at the future, bad, bad, bad. Look at the past, nothing's happened. What's going on? Troubled me a while. And then I remembered greenhouse gases aren't the only thing that's changed over this past century. So this is from a study that Gabriel Vecchi, who's at the University of Iowa now, but previously was at Princeton, and I did, I guess, 6 years ago. What it is a compilation of the response of this quantity power dissipation index, which is a convolution of frequency, intensity, and duration, but it's dominated by the duration and frequency of the strongest storms because it's wind speed cubed. And the black line is how climate models say this quantity should have changed over the past century. Over the past century, this quantity, the same climate models that say that we should get an increase in hurricane intensity going forward, show this black line here where there's actually no real change in this combined measure of hurricane activity. In fact, there's just this gouge taken out of the end. Right? You see this flat line and a gouge? And that was a weird shape. And then we said, okay, is that greenhouse gases doing something weird? In fact, if you take these same models and you say only increase greenhouse gases, they tell you should have started to see an intensification in the Atlantic. It's the non-greenhouse gases. Over this past century, and more recently over the past 70 years, there's been big changes to aerosols over the Atlantic. For those of you who came to Amy Clement's talk last week, she talked a bit about this. After World War II, big industrial buildup in the United States and in Western Europe and even in Eastern Europe that was fueled in large part with coal. That coal sent stuff up in the air. Remember acid rain? It's not just the rain, it's also the clouds and the soot and the dust. And what that did is that it, over the 50s, 60s, 70s, it masked the Atlantic, led to relative cooling. And then, as clean air regulations kicked in into the 70s, 80s, 90s, that pollution got pulled off the Atlantic, leading again to relative warming. And so this gouge taken out at the end on what should have been overall increase is the effects of particulate pollution and its interaction with clouds and then its subsequent removal. What our climate models are telling us is that even though we expect an intensification to go on in the future, we also expect not to have seen it yet. That's really problematic because it makes it hard to, we trust our models when we see what goes on in observations. Here the models are saying you can't see it, and we don't see it, but there's many ways to not get a signal. It doesn't have to be the way that the models show. Now, one bit where I start thinking the models may be actually right is if you compare this prediction of what we should see with the corrected major hurricane record. And I'm going to toggle it back and forth. You see that black line with a gouge taken out of the back? And look at the red line with a gouge taken out of the back. See that? There's a flat and a gouge. So it may be that what went on in the Atlantic is signaling the superposition of greenhouse warming and then the aerosol masking of that signal just when it should be biggest by itself. But we really need to understand then the response of hurricanes to these other forcing agents. One of the forcing agents that is relevant, I mentioned the particulate pollution, but there was also other things going on over these same years. Alan's here. This is his plot. Over this period in between about the 60s, 50s, and more recently 91, the last major explosive tropical volcano, Pinatubo, there was a series of volcanoes that shot all sorts of gunk into the atmosphere, but in particular, they put sulfur into the stratosphere that turned into sulfate, and it started scattering back out to space. Give it long enough, these volcanoes will change CO2 and they act in a whole different way, but we're talking about short time scales, right, where sulfate is the main driver. They acted to cool the planet. And so one of the things that Wenchang Yang, I saw him, there he is, and Stefan and Larry Horowitz at GFDL and a few others tried to do is ask, how do these volcanoes impact hurricanes? And the first thing we noticed is that although volcanoes are all volcanoes are all very different from each other. And so here is the zonally average, the east-west average, and this is a function of time starting in the 50s, 1900s, 1850s, of the volcanoes, the volcanic forcing. Pinatubo is the best observed volcano, and it's often taken as sort of prototypical of what volcanoes should do to climate. But if you look, the meridional structure of past volcanoes, at least over from the mid-19th century to the present, does not look like Pinatubo except for Pinatubo. Pinatubo hits both hemispheres at the same time. It acts to cool the entire planet. It's a very symmetric forcing. And meanwhile, other volcanoes, Agung, is very strong in the southern hemisphere. Santa Maria here in 1902 was very strong in the northern hemisphere. And so the question we asked was, to what extent is the volcanic response in tropical cyclones dominated by the cooling effect that they all share? And to what extent does it depend on the meridional structure of the forcing, which is different between every volcano? And so Wenchang ran a number of ensembles with the climate model where he repeated the same volcano over and over and over and over again. And we could see how the climate model responded to these various volcanoes. And this is, here are maps of the response of hurricanes to Pinatubo, that symmetric volcano. Agung, that southern hemisphere volcano. And Santa Maria, that northern hemisphere volcano. There are some similarities in all three of them. They all increase the hurricane activity near the dateline, right? But beyond that, they are more different from each other than they are similar. And it becomes very clear when you look at the zonally average hurricane activity. Santa Maria leads to a decrease in northern hemisphere hurricane activity, cyclone activity, and an increase in the southern hemisphere. This is associated with a southward shift of the tropical rain belt. Agung has relatively mixed picture, but there's a decrease in the southern hemisphere and there's a significant increase in the northern hemisphere that is also associated with this meridional shift. And Pinatubo, which is our best observed poster child, doesn't do anything significant. There's no signal outside of the noise. And so this is saying is that when we start thinking about these non-greenhouse forcings, we need to start looking at things much more carefully, because greenhouses are all the same. Greenhouse gases, well-mixed greenhouses are all the same. It appears that volcanoes are fundamentally not the same. Okay? All right, so I talked a lot about hurricanes, and I think I painted the picture that we should see, perhaps over this coming century, an increase in hurricane activity along the U.S. Not over this century, at least when it comes to intense storms. But is that all we can say? And it turns out that we can say a lot more if we start thinking about the ways that hurricanes affect us. Number one of the big ways that hurricanes affect us is by raining on us. All right? Think about Irene, and think about Harvey, and think about Imelda. There's many others. As you warm the planet, and as we have warmed the planet, the holding capacity of air for water increases. It's a Clausius-Clapeyron relationship, and it increases about 7% per degree. So a hurricane that is in every other way the same should give us more rain. There's also issues with regards to people moving on away towards the coast and urbanization. And then the other final piece is sea level rise. Sea level rise is clear. We know why it's happening. We know it's going to continue to happen. And unless hurricanes go away, the same hurricane will carry more of a punch. So here's just some brief discussions of this. It's been known for quite a while. Here's a paper led by Tom Knutson in 2013 that tropical cyclones, and this is sort of the radius at which you average the rainfall along a tropical cyclone and how the change of rainfall in that cyclone in the percentage goes. And if you go look within 100 kilometers of the center of the cyclone or 200 kilometers, this model says that you should get closer to 25 to 35% increase in the rate of rain from that same cyclone. And what's interesting is this is the Clausius-Clapeyron rate, the rate that you should get from just moistening the atmosphere, and it proceeds at a higher rate. There's a paper about to come out led by Maofeng Liu that explains this. It's very simple, but I'm not going to blow his story. It's pretty neat, and we understand it. So this looked like a mystery, and it has a very, very, very simple solution. But storms will get wetter. Not only will they get wetter, it seems that they have begun to do so. Remember 2017, we had Harvey. This is BP headquarters. This is our colleague Cindy Yielding. This is her house. This is Harvey. Again, beautiful, but not so nice, right? A group of us, right after Harvey happened, decided to say, what can we say about the role of climate change on Harvey? And so we proceeded on a path of previously published methods. We published these methods before, but we did it intensively right after Harvey. And what we found is that climate change increased the intensity of Harvey's rainfall by somewhere in the tens of percent, 10 to 20%. Say 15 is the mean. And that increase in intensity translated as an increase in exceedance probability. These are two ways of saying the same thing, of about a doubling or so of the likelihood of as much rainfall as Harvey gave. Harvey was made more intense, or you could also say it more likely, by climate change. Now Harvey, though, and this is to me more interesting, was also affected by another anthropogenic factor. So Houston is a city. For any of you that have flown into Houston, it's got like 2 or 3 or 4 downtowns, big buildings. Outside of Houston, it's grassland. The winds that blow with moisture from the ocean onto land and encounter Houston don't encounter grasslands. They encounter a city that causes turbulence. And so we went to assess, this is with my colleague Wei Zhang and Gabriel Villarini and Jim Smith at Civil. We assessed the extent to which the rainfall from Harvey was modified by the urbanization of Houston. We took a model, ran Harvey on it many, many times in many different situations, and then we replaced in that model Houston's landscape with grassland. And what you find is that when you include the urban piece, you get more rainfall over Houston from Harvey than when you don't. So in addition to increasing greenhouse gases, warming the planet, and increasing the rainfall from Houston, this urban effect seems to have enhanced the Harvey's rainfall. These are not alternative explanations. They're happening at the same time, and to a certain extent for the same reason. This is town built on fossil fuels, right? Not only that, when you urbanize, when you pave over, any of you that have a driveway, you have to get permits before you pave, right? And now they have the new pavement that allows infiltration, but you can't do that with a house. A house, by necessity, has to make things run off. When you pave over, you increase the fraction of rain that doesn't infiltrate. And that over Houston had a massive effect on flooding. And it depends on where you are. If you look at a rural place like Cypress Creek, primarily the effect of urbanization was the rain, not the runoff. But if you look at a more urban place here like Sims Bayou, the runoff part was a massive impact of urbanization. We have all these effects going on at the same time. These hurricanes are going to continue happening. They're going to happen over warmer waters, and as we move into cities, they're going to encounter urban environments. Finally, and then just stop, this is one of my favorite pictures. Sea level has risen. We know why. Sea level has risen because we've melted land ice and pumped water out of aquifers. And it has risen because the ocean has been expanding due to thermal expansion. That's what these three lines show. And we've closed a sea level budget. The fact that this purple line lines up on this black line says we've closed a sea level budget with independent measurement. I think it's one of the most beautiful plots. We don't have enough time to talk about it. But sea level is going to continue to rise, and it's not going to rise uniformly. The east coast of the US, and in particularly the mid-Atlantic, we're in the mid-Atlantic, should see a larger than average sea level rise. That's modulo the relative melting of Greenland to Antarctica and the gravitational effects there. But as sea level continues to rise, the storm surges that a particular storm gives us, even if the storms themselves do not change, are going to be more impactful. This is the things that we need to take into account. All right, so this is sort of a summary. Multiple forcing agents and variability may have masked 20th century intensification of Atlantic hurricanes, but we expect it to happen in the future. That means that we really need to understand the mechanisms behind that and really probe our models and our understanding so that we can build that, not on empirical evidence, which we're saying we can't get, but on a true solid foundation. Harvey was wetter from global warming. Urbanization also increased the rainfall from Harvey. How do these two effects interact now, and how may they interact in the future? I think this is a question that a place like PEI can help answer. There's a projected increase in East Coast rainfall and European storms of tropical origin, and both the top speeds of tropical cyclones and the rate of rapid intensification should increase. Finally, sea level rise and demographic changes are probably going to be some of the bigger factors that play into our risk. And that requires a fundamentally interdisciplinary approach to understand. And thank you to the people that floated some cash. And sorry that I went a little too long. Thank you. Alan.
You didn't really mention trends in wind shear. I was wondering how that will affect the changes of hurricanes. And does that have to do with the shifting from the northeast of the patterns?
So the question was about wind shears. This is a change in wind with altitude and how that might affect hurricanes. So there is some impact of wind shear in. So models are saying wind shear should increase in parts of the Atlantic and decrease in others. And that will shift the location of genesis. And one of the ways is that it shifts the location of genesis towards areas where storms are more likely to recurve. Also associated with those shifts in shear are shifts in wind velocity of the steering winds. That's another factor that changes the storm trajectories. So the question is, what does the community as a whole think about the impact of tropical tropopause temperatures on hurricane intensity? And I don't think that we have a consensus. We have a group of us that seem to not be so convinced based upon the evidence that we've looked at. And then you have another group that seem to think that a cooling over the historical era of the tropical tropopause has been very important to the intensification of hurricanes that we've seen. Part of the issue is that cooling of the tropical tropopause is not entirely clear that it's real. Is that a way to say it politely? Yeah. So. Yeah, so there are two effects of urbanization that we were able to disentangle for Harvey. One of them is relatively straightforward. You take soil and you replace it with something that doesn't allow infiltration. That increases the amount of flood you get per every ounce of rain. Okay? easy. The other piece that was even, to me, a little bit surprising, but there's evidence for it in, at least with regards to convective storms. Jim Smith's written a bit about it in Baltimore, but there's also some work in St. Louis. There's a lot of studies in St. Louis. But there it seems to be due to the heat island effect. Here in Houston and with Harvey, it wasn't the heat island effect. What it seems to be is these winds are blowing in for, okay, I'm trying to get the right angle. So here is Texas coast, here's the Gulf of Mexico. Winds are blowing in nice and smooth over the ocean, picking up moisture. If this was grassland, they would largely skim over the land. And there would be some turbulence, but little by little you would spread out that rain over a longer fetch. If you place a comb of city on the way, as these winds make it on shore, they start hitting these mountains. You generate turbulent kinetic energy. That acts as a trigger on localized convection. And you dump more of the rain over the city and nearby than further downwind. That's sort of the second effect. Yeah.
Could you elaborate on your answer to the first question, that the increases in wind shear may affect which into the curve? Does that mean we're going to have more or fewer hurricanes hitting the east coast of the United States?
So I think to be very definitive about whether we're going to have more or fewer hurricanes hitting the United States on the East Coast is a little tough. It depends on which models you look at. But the way I'm thinking, and I didn't get into this very much, but I've started to think more of hurricanes as a series of chain transitions. So there's this thing in the hurricane community. There's about 90 hurricanes a year all around the world, and nobody knows why. It's not 1,000, it's not 5, ever. It's somewhere between 70 and 110, and there is nobody who can explain to you why, or at least nobody can explain to you why and know what they're talking about. And so that's a big question. Why are they 90? And one of the things that seems to perhaps explain it is that, and it's not explaining it, it's just putting another turtle underneath it, is that you have about 800 seeds of storms on our planet, and each one has about a 10% chance of forming into a storm. And if you split the problem into a transition probability, a genesis probability, and a seed probability, then now you're talking about more common things. And we think we know what the probability of transition is. You can do that all the way down. You can say once you have a storm, the storms that hit the US are a fraction of those storms, and you can think about what modulates that probability. And what's going to modulate that probability is where the storm forms, because the typical winds will tend to steer a storm that forms in one place one way and another place a different way. And also what sort of winds they encounter along the way. If you change the winds, they will funnel them a different way. And for the Atlantic, we think that both the changes in where the storms form and the average winds, plus the changes in the winds themselves, are contributing to the changes in track. So, yeah. Yeah, Alan.
Are storms moving more slowly, and are they lasting longer?
So, yeah, so there was a study that got a lot of attention right after Harvey by a colleague, claiming that storms around the world are moving much more slowly. There have been a number of comments written on that paper, all of which point out what a layperson would probably see in that paper, that there's a transition around the mid-60s, which is the beginning of the satellite observing era. And so you have two climatologies of storm speed, one period where you're moving more slowly and one period where you're moving more rapidly, coinciding with the transition of satellites. And so I don't think that there's really any presently generally accepted evidence that storms are moving more slowly. Not only that, the modeling studies have either found no change in wind speed or perhaps a slight increase in wind speed. Not wind speed, translation speed. There's a paper by Tom Knudsen where he looks at eight models, and 5 models show nothing, and 3 models show an increase in speed. So I think that, now if you only want to cite that one paper, then there's evidence.
So what's the status of all the papers explaining the droughts. Are they an embarrassment? Is it good science?
No, I think they're good. I think when you try and understand, I mean, if you try and explain something interesting, why is there a drought, right? It makes you think differently than you were originally thinking. That explanation, the number of explanations that came out, each one had a different prediction of what should happen. And so now the fact that the drought has gone away means that we have only some of those potential explanations are still viable. So I don't think that, I think it's great to be wrong.
So you think the drought is real? You're defining that as here, but the East Coast.
It's a really small sample. The U.S. isn't that special. Sorry, we are exceptional. But, yeah.
Why are there so few cyclones in the South?
Oh.
I just looked it up on Wikipedia and said it's because it's very strong vertical wind shear, but it doesn't say why.
Well, it doesn't say why. That's good, because then I get to explain it. So you can see over here, there's not very much tropical cyclone activity in the South Atlantic. The proximate cause is that there's a lot of wind shear. The air tends to be somewhat dry in the middle troposphere, and ocean temperatures are warm but relatively cool in the spectrum of warm. But that's the proximate cause. I think the ultimate cause is the Atlantic is a unique ocean in that it is the only ocean that moves heat northward all the way from the southern hemisphere to the northern hemisphere. So in the South Atlantic, unusually, heat is moving from high latitudes to the equator. And then it moves beyond into the North Atlantic, that heat. And so the ocean is fluxing heat out of the South Atlantic. It doesn't build up. And so one of the things that tropical cyclones do is that they take heat energy from the ocean, store it in water vapor, bring that energy into the upper atmosphere, release that energy through condensation, and then let that radiate to space. You don't really have to do that in the South Atlantic. That's one way I think about it. You also don't, the other thing is you have a relative absence of hurricane activity over here and over there. These are areas of descent in atmospheric circulation. These are where you have these stratosthecs. And sort of, it's not, and so each one of these areas has its own special thing. Now it doesn't, I don't think that if you came back, I don't know, how many million years ago did we think that there was overturning in the Pacific? I don't remember my paleo calendar that much, but if you came back at one of those years when there's overturning and sinking in the North Pacific, maybe there are hurricanes in the South Atlantic, but not in the South Pacific. Maybe. Brian?
If the Gulf Stream were to stop,
Yeah.
how would that change the picture? If Northern Europe was cooler?
So with the Gulf Stream to stop, would that change things? I'll start by giving, I think I'm going to paraphrase Wunsch's two-sentence response about the Gulf Stream shutting down. As long as the winds are blowing on our planet and the planet is rotating, we will have a Gulf Stream. Okay? It may be stronger or weaker, but we will have a Gulf Stream. But I think that a reduction in the northward heat transport into the Atlantic by whatever means, either in terms of the vertical transport or the horizontal transport, would reduce hurricane activity in the Atlantic. And that's one of the theories out there as to why you have these multi-decadal variations in hurricane activity, that the meridional overturning, the formation of deep cold water and return below, and the northward movement of warm water to supply it, has periods when it is stronger and weaker, and the whole climate complex changes in response to those so as to make certain periods more active and other periods less active. There are other interpretations, and the extent to which that is the dominant mechanism of what we've seen over the last century also remains under debate. So, yeah.
Can you comment on why the models predict such longer tracks than the observations?
Yeah. So why do the models predict such longer tracks than the observations? In part, it's the way we track the storms and the observations track the storms. The models here, we track the storms from the moment that the storm starts to spin through when it becomes really tropical and symmetric and beautiful, all the way to after, while it's an extratropical storm and then goes into the high latitudes. A lot of the observational data sets stop tracking storms at a certain point. So especially in the southern hemisphere, once a storm hits 40 south or so, there's nobody interested in it anymore. And so these observational records that we use are the side effect of weather forecasters tracking storms to make weather forecasts. They are not the goal, right? And so we're working with things that are not climate data products and trying to retro-engineer them into climate data products. And so these are not exactly the same. Yeah.
So I assume yesterday some reporter called you up and said, look at Lorenzo, it's the strongest hurricane in the eastern Atlantic. Is that a sign of global warming? Do you say, well, what about the drought? Or do you say, how many more Lorenzos do we need to get a significant signal?
So fortunately, or unfortunately, life was complicated, so I didn't have to answer any reporter question because I didn't answer my email yesterday afternoon. But I think that is a tough question, right? We have a pretty decent expectation that over the 21st century, hurricanes should get more intense. It's not clear what has happened. We know that since the 70s, hurricanes in the Atlantic have gotten very intense. But there's multiple possible explanations for what drove that change. One of them is global warming. But another of them is the clearing of the aerosols, or the reduction of volcanic activity, or the dust coming off the Sahel, or these variations in the Atlantic meridional overturning, or all of them at once. And so the part I'm confident about, which is the intensification over the last few decades, I'm not confident about the cause, right? If I could tell you confidently that storms have gotten really strong over the past century, then that would be one thing. But we know that 1933, even with bad observing, was off the charts. And 1887 was also a crazy year. But we don't know what we missed. And if you look back in the paleotempestology record, which I haven't had a chance to talk about here, which allows us to look back thousands of years at certain locations through sediments, we seem to be in a multi-centennial lull right now in parts of the Atlantic. We're at low levels relative to the middle of the last millennium, going back into the beginning of the Common Era. So saying it's global warming makes me have to sweep a lot of things under the rug, which I'm not comfortable yet doing.
Let's take one last question.
You talked about hurricanes getting wetter in the future, and you also showed that map of pretty where predicted hurricanes are going to be showing up in the next century with a lot of those black spots, places that haven't been before. All of it looked to me like they were more inland.
Yeah.
So do those two things add up to hurricanes in some sense playing a qualitatively different role in the distribution of fresh water in those places? Like, I mean, this is a naive question, but it seems like there are these massive salt to freshwater conversion machines. It probably doesn't matter that much when they're raining on the ocean or when they're raining on an island, but if they're pushing far inland and dumping more water, does that become a meaningful influence on where fresh water is?
So I think that, so the question is are the changes in hurricanes going to affect land hydrology in short, right? And I think the answer is probably yes. That is one of the concerns, that they would increase sort of flood, right? Because either our infrastructure or the geology is such that it's not used to having these big tropical sources of rain falling every fall. However, and this is something I didn't talk about, but Justin Sheffield, there was a student working with Justin Sheffield, right now the name eludes me and I'm really, really sorry, terrible, who found really nice results where hurricanes in the southeast US were one of the key ways to break drought, right? Because if you have a long period without a lot of rain, all of a sudden you put a hose on it, that kicks off the same positive feedbacks that sustain a drought, you can have them go the other way. And so there's a potential for not necessarily altogether negative changes coming from storms being wetter. Yeah.
Thank you.
Thank you. There's somebody going to use this building at some point, right?